Hello, welcome to the 11th plus session of Algebra 1 course. This is Shovik. Right now I'm doing my research on cross-union matters. So in today's last session, we can do two things. First of all, I was going through all lectures that has been done by sir. So there is one topic, namely the tensor product, and I feel this particular topic, tensor product, I should go through this tensor product thing because initially it is very abstract for most of the beginners. So that's why I have decided first we go with the basic tensor product, then we'll solve some problem with the tensor product, and finally if time permit we shall go with um, assignment 11 question answers. Okay, quiz 1 question answers. Okay. So sorry, assignment 10 question answers. Sorry, quiz 10 question. Sorry. So okay, so let's okay. So let's begin with. Am I audible?
Yes, what do you?
Okay. Can you see the screen?
Yes, yes.
Okay. So just tell me one thing. Actually, I was going through the all lectures of Sir. So I think except uh, going through the assignment, I think it's better to go with the tensor product. What do you think about it? Because I feel that
Yes,
tensor product is something abstract from other portions. This initially tensor product is quite abstract. It is difficult to feel actually the tensor product. That's why I'm thinking to start tensor product first, and then type over then assignments. But my main target is to do tensor product and at least solve some basic problems in order to have some feeling the tensor product what is going on suddenly from those structures and all. Okay, so that's why I'm thinking to start TensorBoard today. Okay,
yes. That will be fine.
okay. Okay. So tell me one thing. Hmm, um, okay, just asking one thing. Have you started TensorBoard before? In the search class.
Mhm. I have read I have been read up to pre-module and finitely generated module and their properties.
That is okay. Okay, that's okay. But have you started Tensor product? Basic at least. Any rough idea do you have? Loudly, I don't get you actually.
No, sir.
Okay. No. Okay. Okay. So let's start from very beginning.
Sir, after this course, if some confusion or conceptual asking or arise, then how can I contact with you or how can I reach
Okay.
with
Just
you?
tell
Is it
me.
possible?
Yes, just tell me one thing. When is the exam?
Hmm.
When is the exam?
Exam is around October 29.
October. Okay. Mm, mm, uh, One second. Yeah. Okay. So the thing is, possibly the next week will be the last class, right?
Yes.
Okay. So after next week, there will be one more class I will take of 1 hour. Okay.
Okay.
After next week,
Okay.
that is the third week. Okay. So there will be 1 hour live session. So you can uh, keep your doubts together and I will take the live session so you can ask
Okay.
me. Okay.
Okay.
Okay. So the next to next week, let me check the date. That is 20th October, and the exam is 29, right?
Yes.
Yeah. Okay. Fine. Okay. So first of all, Okay. So before starting the tensor product, let me tell you very clearly that tensor product, I mean, the thing is, suppose we have some module M and N. Okay, listen carefully. Okay, because
Yes.
this thing is very abstract, so you need to listen first. Suppose M and N are two some modules. Okay,
Yes.
some modules, some A module. Okay, and from this we are defining some new module. Okay, some new module having some properties. Okay, but the thing is, this module T by construction is nothing but the quotient of the module M cross N via some equivalence relation. Okay, via
Yes.
some equivalent relation, we're going to construct some module. Okay, so
Yes.
in that module, we can talk about what does it mean by some A cross zero, zero dot, I mean zero dot A dot A, these etc. etc. Okay, of in natural way because it is a quotient module. Okay, but the problem is that the way it is defined, from that it is not directly possible to say something what about, suppose for example we have 1 dot 2. Okay, I mean suppose in the quotient we have the dot, we have 1 bar dot 2 bar. Now the
Yes.
problem is that in usual ring and usual quotients, for example r by I, it is most of the time it is easy, that is what is 1 bar dot 2 bar equal to 0 bar or not. Okay, but in a particular equivalence relation, it is not always possible to say that product of two things is zero or non-zero. Okay, so I mean this is some kind of equivalence relation for which we are getting this type of difficulty, that is we could not determine something is zero or non-zero because of the particularly chosen equivalence relation. So in order to tackle that thing, we have some more properties. Okay, so the thing is, we have some properties P along, it is some property. Okay, and we have some module. Okay,
Okay.
which is some kind of quotient of M cross N, and then we will see that 1 dot 2 bar equal to 0 or not. This depends on the particular property P. Directly we can't say anything. Okay, this first thing you need to realize, I mean this is the first thing you need to keep in mind. And secondly, what do you know, one thing is that suppose you have some map R1 to R2, some ring homomorphism. Okay, and
Yes.
then if we see that for any xy belongs to I, if that under this map fx equal to fy, then we say that this map f induces a unique map r by I to R2 such that this diagram commutes, right? Correct?
Yes.
Okay. So also we can do that thing R1 by I to R2, and we are defining this relation if R bar goes to FR. That's all. I mean that's the map. Okay.
Hmm.
So in the right portion, in usual situation, the checking the well-definedness of this map is not very difficult. But in case of tensor product, I mean tensor product comes from a particular equivalence relation. With respect to that particular equivalence relation, it is actually very difficult to it is actually very difficult to directly checking the well-definedness of some map passing through quotient. Okay, and in order to tackle that problem, we have some more property, call it P2. Okay, so while working in tensor product, we need to always use these two property P and P2. I mean, okay, we are going to see this. Okay, but the thing is, tensor product is something which is by definition abstract, and in order to work with tensor product, we need to use some two or three properties, and that two three properties will solve any tensor product problem. Okay, so in tensor product, nothing can be done directly by definition. Always you need to use some property. Okay,
Okay.
that is first thing which differs tensor product from the other parts of abstract algebra. Okay, so whenever you have some problem in tensor product, don't try to solve it directly. Directly, it is impossible to solve.
Using definition.
Sorry, huh? Huh?
Directly using definition, it is.
Yes, right. It is impossible to solve using definitions. For that, you need to use some properties always. Okay, so so
Yes.
this is the first thing I need to say. Okay, so and the second is that I have said some properties. Okay, those properties are known to be universal property. Now the point is that if you have not heard that of universe property, the keep in mind it is some kind of property which satisfies the tensor product. I mean tensor product satisfies this type of property. That's all. Okay. I mean don't go with the universal wide universal, leave it. Tensor product satisfies this kind of property. Okay, that's all. And okay, so now I'm going to write some proposition, and most obviously you will think suddenly why this proposition is coming, but keep patience. First, I write the propositions. Okay, I am not going to write first. I'm just going to write a proposition, but I'm not initially going to write the proof of the proposition. Okay, after going through some propositions and some easy consequences, first we go through some problems, then we'll come back to solving the. I mean to go to proof of the proposition. Okay,
Okay.
so that's all it is. And okay, while writing the proposition, you might think that suddenly what abstract thing is coming, but don't worry, keep patience. Okay. So, let M and N be A modules. Okay. By the way, should I increase the font or this font is fine?
Yes, sir.
Should I increase the font? I mean the font, or is this fine?
No, okay, okay. It is compatible with site.
Okay. So let M and N be to A modules. Okay. Then here is the pair P comma Z consisting A module B and
T in open bracket T
yes,
and what?
yes, yes.
T and T comma.
G this
Acha, okay,
F,
okay.
yeah, and then a bilinear map from F M cross. Sorry, one second, it's my mistake. A bilinear map G. By the way, one thing, I don't have any power backup, so if in between suddenly I got disconnected, kindly wait patiently. I will join again after 2 or 3 minutes. Okay.
Okay, okay.
And there is something I have written like a bilinear map. Kindly wait. After writing the position, I will explain what does that mean. Okay. The statement is quite big. First, for writing the statement, first write, then I will tell you. For writing the statement, after the writing this way, I will explain what does the statement mean first. Have you written down the statement?
Yes, it is finished written down.
Okay, so first let me explain what does the statement means. Okay. So there is some word called as a bilinear. Okay. So what does that mean? Bilinear map mean? What does that mean? So bilinear map, I mean linear map means linear in each component, right? Bilinear map means linear in each component. Sorry, bilinear map means linear in each component. That is, suppose any map G from M cross N to some module P, some module. Okay, these are not connected with these A, B, C. These are some module M and P. Okay, then G is said to be, and everything here is an A module. Okay, then G is said to be bilinear or A bilinear if G is linear in each component. That is G of M1 plus M2 dot M3 into G M1 M3 then G M2 M3 G of M1 comma M3 is equal to G of M1 M2 G of M1 M3 G of A M comma N is equal to A G M comma N is equal to G M comma M. If these relations hold, then G is said to be a bilinear or bilinear map. Okay, this is what the bilinear map means. Understand?
Yes.
Okay. So this is one thing. Okay, so now let me first extract what does extract tell. So this is telling something like that. Suppose we have some module M and N, and both are a module dash. Okay. Then this is saying there is a pair T comma G. One second. Yeah, then it is saying there is a pair T comma G consisting of an A module T, then there exists T which is an A module, okay, and we will have some map M cross N to T G. This map will be some A bilinear map, okay. This some map, don't bother about what is the map, okay. For time being, don't think about that. There is some map G, okay. Now it is given that with respect to the following property, you are seeing following property. It is some map which satisfies certain property. That is, if we have any A module P and any A bilinear map F, it is also a bilinear map. Okay, then there exists unique map F dash such that this diagonal commutes. That is F dash composed F is equal to F dash composed is equal to small f. Okay, and if this pair, this is first portion of this thing, and if this pair P comma G satisfying this property, then this pair is unique. That is, we will have an isomorphism. That's all. Okay.
Sir,
So
yeah, M and N are A module, and
yes,
T is another A module. Okay.
no, T is not another A module. Look at the statement. What is this we're saying? Suppose M and N are two A modules. Here exists a T module. It is not another. It is some A module connected with M and N. Understand? I mean, it is not random thing. Understand?
There exists a pair T, comma G consisting of an A module T.
Yes, means T is an A module. Okay. I mean,
Exact.
it is not random thing. That's the point.
Okay.
Yeah.
Achha.
And some map G from M cross N to T, which is an A bilinear map. Okay. This is something exists such that we satisfy some properties. What is the property? If we take P, any module, okay, and M cross N to P is of any bilinear map small f, then there exists a linear map. Obviously, you are in modules, so everything is linear or bilinear. Okay. Then we get a unique linear map from T to P such that this diagonal commutes. Okay. So this is the property. It is satisfied. Okay. And the thing is, second portion is saying such a pair T comma G is unique. Forget about uniqueness right now. First, you tell me, do you understand the first property which is satisfying? I mean, if you couldn't understand, probably tell me. I mean, the property is that we have some M and some M mod n, which is both A module, and there is some module T, okay, and some bilinear map G, which satisfies some property. What is the property? If we have any arbitrary module P and any map small f from M cross N to P, which is a bilinear map, then this bilinear for this bilinear map, we will get a linear map from P to P such that that diagonal commutes. Okay, so this is the property P comma G here is satisfying. Okay, this is a property. Okay, understand? So that is the property. Okay, I mean, it's of course there's nothing to understand, but I understand that. Uh, if, I mean, okay, just keep patience. Soon we will see some examples, consequences. You will then you will understand how to use this or what is this actually. Okay. Now the point is that okay, one second. Okay, so first question is what is this T? Okay. So let's get into first T. P and G we need especially. Okay. So look, we have some module Mn and A module. Okay. Then let T be the pre A module over M cross N. Do you understand what does this line mean? M cross N is an A module. Let C be a free A module over M cross N. Do you understand this? Okay, let's make it easy. Free A module with basic. Now tell me, do you understand this meaning of this line?
With basis M cross N.
Yes. M and N are some free modules. Okay, we have some elements from M, some elements from N. Okay, we have some elements. Okay, for operator with some elements. Now we are making C a free module, free A module with basis M cross N. I mean, M cross N is a set, right? I mean,
It is a set, huh? Yes, yes.
yeah. So in vectors, we have some set. Then we can consider some vectors with having the basis that set, right?
Hmm.
The same thing here. That means what? What is the elements of C? How elements of C look like?
Say look like elements of some A1 from A summation M1
Yes,
M. Yes, yes.
correct, correct. Yes. So these are elements of C. Okay.
Okay.
So these are C. Now, so we are considering D, which is an submodule of C. And how D is considering? D is constructing. D is some submodule generated by all elements of C of the types. Now this portion you may get some difficulty, but wait. So look, one thing is that. So suppose, I mean, for example, suppose we have a ring R. Okay, then ideal can be constructed by taking some. Ideal can be a generating set. I mean, generator. I mean, we can consider ideal generator by some element is smaller, right? Same thing
Yes.
in the module also we can consider some module of C, and that module capital D is generated by some particular type of elements of C. That is possible. That makes sense, right? I mean, the thing is, if we call this element capital X, capital Y, capital Z, capital W, that means what? D is a submodule of C generated by this type of element, right? Correct? I don't be silent. If you have problem, please tell me. And okay, one thing, generated by all elements of the type this. Okay, here everything is varying. X, X dash, Y, Y dash, A. Everything is here is varying. Okay. Do you understand what does this mean? D is a submodule of C generated by all these elements of this form this. Okay, that's all. Nothing more than that. Okay. That is any element of D. Sorry, any element of D is linear combination of this X, Y, Z, and W. Understand?
Yes, sir. What
Yes.
is missing that point? X plus x dash comma y. It is goes to x y and then x dash
No,
y.
no. It is not good. It is minus. I mean, we
Okay.
have yes, x plus x dash comma y minus x comma y minus x dash comma y. Similarly, here everything is minus. These are just elements, right? We are a module, so minus makes sense, correct?
Yes. Yes.
Yeah. So these are some particular type of elements where this x dash y dash x y a capital A everything is varying, small everything is varying. Okay. So there is some particular type of element by which we are generating the capital D. Okay. One second. Do you understand?
Yes.
Now these some submodule. So we can talk about quotient, right? We are defining P to be the quotient C by D. Okay. We are defining this P to be C by D. So that means what? Uh, I mean, so we are defining C to be C by D. That is how the elements of P look like. How the element of P looks like.
Mhm.
Tell.
Yes.
Sum, summation
AI,
AI
comma m plus m my m comma ni
whole bar,
and
right?
plus yes,
Yeah. Okay. So
plus element of plus
yeah,
d.
that is the whole bar. Okay. And in this particular case, I mean, in this tensor product situation, we don't use this sign bar. Okay. Instead of bar, we are writing m cross n means this means nothing but m comma n plus capital D. Okay. This is m cross circle small n. We are writing this thing as m plus n plus g. Okay. Understand? This is a
Mm,
notation. So M tensor, so this is known as the tensor M tensor n is nothing but M comma n in the quotient submodule. Okay, this is a notation. Understand?
yes.
Okay. So the elements of P are of the form what? Summation AI, Mi, tensor AI, right? Everything is finite sum. Okay,
Mm,
and moreover, this Mi, I mean, moreover M. So obviously, since any elements are of this form, so this set M tensor n generates P, right?
mm, yes. Repeat one.
Yes. So we have some notation for M tensor small n, right?
Mm,
And by this notation, we are getting that any element of capital T are of this form summation ai mi tensor ni, right? So
mm,
from this, what we can say? We can say that P is generated by the elements of the form
mm,
small m tensor small n, where small m goes to capital N and small n belongs to capital N, right? This set, I mean, this collection generates capital D, right?
yes.
Understand?
Yes.
Yes. So this is some T, okay? And
Mm,
moreover, since T is nothing but C by D, and so from M cross N, To C we have some obvious map, and C to C by D we have some quotient map, right? And why it goes M comma N goes to M comma N goes to M tensor N, right? Yes.
Yes.
This composition we are denoting by small g. So that is to say, small g is a map from M cross N to C. Small n comma small n goes to small m tensor small n. Okay, this is the map G. Understand? And the module T, this module T, we denote it as capital M tensor capital N, and tensor, within tensor in suffix we write the ring small a. This is the notation. Capital M tensor capital N, and under the suffix of a tensor sign we write the small a. Okay, so this is the ring M tensor N. Do you understand? Till now, do you understand?
Sir, m comma n go map to m comma n a ai m comma n is it
Can you please repeat? I didn't get you actually.
yes m cross n to c then it is defined by m comma n goes to ai m comma n is it
So what is AI? I mean, what is AI?
c element of c are look from ai.
Yes, yes. Elements of C are of the form summation AI, Mi, comma Ni, right?
Hmm,
Correct.
yes.
But anyway, Mi, comma Ni is an element of C, right? Because we are taking A to be AI to be one in that case, right?
Okay, 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 okay.
Yes. Understand? Do you understand?
Yes.
Okay. So till now, what we get? Till now, we get some capital T, which which is generated by the elements of the form small n tensor small. So the small m tensor small n, and we have some map small g capital M cross capital N to T, sending m comma n goes to small m tensor small n. Okay, and this T we write it as m tensor n tensor over capital. Okay, now so till now what we get is the following, that is m tensor n a. This is generated by small m tensor small n. I mean, okay, and we have some map G from this to this, where small n comma small n goes to small m tensor small n. Okay, so this is our T. This is the map G. Till now, do you understand what was going on? Don't hesitate.
Yes, yes.
Okay. Now, okay. So now go to the property once. I mean, go to the property. I mean, obviously you have written down the property. So in the property, what you were written there in the property, it was there. There exists some module capital T and some bilinear map G, right?
Yes.
G is given a bilinear. Okay, so now we need to prove the bilinearity. Okay, that is, we need to check is linear in each component or not. Okay, okay, but before going to this, we need to have some simple observation. Okay, okay, so now let's go back to the construction of the module capital T itself. Okay, so C was the free module and D is the submodule of C generated by the elements what? X1 plus x2 comma y minus x1 comma y. Let me write it down again. This is one type of element, another type of element. Okay, so what I mean, in your mind, it may be going that why you are suddenly considering this type of element. I mean, this is what the tensor product it is. Okay, I mean, don't right now don't wait into the reason why we are sending out by this type of element. There is my advantage of doing that. Okay, right now it is not possible to understand unless and until you will get have some problems. Okay, and also the tensor product thing actually apart from algebra, it is used in topology also. So it has actually huge application. So particular this type of quotienting out has some advantage.
Okay.
I mean, right now it is not possible to say each and everything. Just go to construction. I mean, don't think why such a construction. There is some construction. You need to understand the construction itself. Okay.
Okay.
Okay. Kindly wait. I said back for 2 minutes. Okay.
Okay. Sir, please show me again the property by which you defined the bilinearity. I missed the page to write down.
Can you see that?
Yes, yes, see that.
Should I go up or should I go down?
Go up, go up.
That's fine.
Oh, sorry, sir. Go down, go down.
That's fine.
Slightly go down.
Fine.
Yes, fine.
Okay.
Okay.
Kindly wait. I said back for 2 minutes.
Uh,
You're under what? কি
মানে এটা যেটা ল্যাপটপে ফেস টু ফেস দেখে কথা বলছে তো
হ্যাঁ
তো সেটা অফ করেছে তো
হ্যাঁ
তাহলে ওটা আমি বের করে দিচ্ছি
হ্যাঁ হ্যাঁ 10টায় না মানে 9:30 খেয়ে নেবো কারণ 9টার সময় শেষ হয়ে গেছে মনটা yeah okay so okay so hmm. So now let's first get into the construction of C by D. Okay. So first of all, what is C? What is C is the pre-module whose basis is the set M cross N. Okay. And we are quotienting that C by a submodule D, which is generated by the elements of the form, right? So this means what? I mean, suppose you have some ring R and some small a belongs to the ideal. Okay, this means what? Capital A is equal to 0. I mean, capital A bar equal to 0 in R by I, right? Please give response. Please give response. Okay, so it's fine. Okay, so capital F is a ring and small a is an element of the ideal capital I. Then a bar is equal to 0 and r by j. Okay. So the same way in the ring C by D, these things are same. This is equal to, okay, exact similar way. This is same. Similarly, the other element, this is same. Similarly, the other two, this is same. Similarly, this one. Right. So this thing holds in C by D. Okay. Now, I mean, if you have any doubt in understanding, please unmute yourself and tell me. Okay. Since you are not responding, so I think that till now everything is fine. So now we have the following notion that small n, since the small n is nothing but m comma n whole bar. Okay. So using that notion, what we are getting for the possibility, we are getting that x1 plus x2 tensor small y is nothing but x1 tensor y plus x2 tensor y. Second one, x tensor y1 plus y2 is equal to x tensor y1 plus x tensor y2. Okay. Third one, x tensor y is equal to a into x tensor y, and this fourth one is giving x tensor ay is equal to a of x tensor y. Okay. So this is nothing, just these are the notation we have introduced the tensor instead of r. Okay. So we are getting three equations. So let me write it down after combining this. One is x1 plus x2 tensor y. It is nothing but x1 tensor y plus x tensor, this one relation. Second relation is x tensor y1 plus y2 is equal to x tensor y1 plus x tensor y. This is another relation. Third one is ax tensor y is equal to a into x equal to a into x tensor y is equal to x tensor ay. These are the three relations that we have in case of these holds in the module C, which is nothing but m tensor n. So tell me till now, do you understand what is going on? I mean,
Last one, I
yes,
not understand. I am not understood last one. Last time, uh,
one
we
right.
have C by D element, and in 4 ways we have written the form, and after that we taking bar. What is the difference?
Yes, can you please repeat and get you actually? Please repeat.
Actually, in first C by D element are such type generating element are form of this four types.
Yes.
After that we taking bar. What is that?
So that's what I said, right?
Which is which is
So,
analogous to
so
R.
if we have a ring, and if
Uh,
you have an element capital A inside the ideal, then in the quotient ring R by I, A bar is
yes,
equal to 0, right?
yes,
It's obvious, right? So that
actually.
obvious thing we have written here. In C by D, we have this
Okay.
we have these four relations, and then we are replacing each and everything by the tensor, by the notation. So then we are getting these last three relations. Understand?
Okay.
No, no. I mean, if you are very how to tell, I mean, don't say just okay. Okay. So, so first relation. I mean, so okay. So first relation. What is the first relation? Is saying the tensor is distributive over the sum. Okay, first and second relation tensor distributes over sum. And last property is saying that I mean this property is the multiplication property for the tensor product. Okay, I mean anyway, don't no need to remember this thing as a property. Just remember these three formulas. Okay, so now these are the relations uh, satisfied by the module capital D. Okay, now if you think that statement we have said that we have some map G and such that this map is bilinear. Okay. Now we need to check that this map is bilinear or not because it is given the property, right? Now, I mean, do you understand what we're trying to do now? We will check that this map is bilinear or not. This is what we want to do. Understand? Yes or no?
Mm, we have to check is this bilinear or not.
I mean, yeah, I mean, that's what it is. Because if you go back to the property, in the property there is some map G and the module T, in our case T is equal to M tensor N, we are taking T to be M tensor N, and the map M comma N goes to M tensor N. We need to check this small g is bilinear or not. Okay? Because, I mean, look at the property. What is the property? Huh. In the property, what is it? In the property there exists a bilinear map G from this, right? So we
Hmm.
need to check the map G is bilinear or not, right? So how to get that? So in order to check bilinear, what we need to check? We need to check G of M1 plus M2 comma N is it equal to G M1 comma N plus GM2 comma N. Is it holds? No. This we need to check. But by definition, what is this? This is M1 plus M2 tensor G, and this is nothing but M1 tensor N plus M2 tensor N. Just now we have seen, and this is nothing but G of M1 comma N plus G of M2 comma N. So this relation is satisfied. Do you understand? If I am not getting it properly, please tell. you are not getting it properly, please tell. So this is the first relation we have checked. The second one is bilinearity. We need to check g of m comma n1 plus x2. We need to check does it is it equal to g m comma n1 comma g m comma n2. But this is by definition for this equal to small m tensor n1 plus n2, and the relation just now we have seen this is equal to, I mean it breaks over the addition, and this is equal to g of m comma n1 plus g m comma n2. So this relation also holds true. Understand?
Yes.
Now the third thing we need to check, that g of am comma n is equal to a g m comma n is equal to this is a m tensor n, and this is nothing but small a into m tensor n, and this is nothing but small m tensor a comma n. So all this relation hold true. Okay. So that means what? That means the map small g is bilinear. Understand?
Yes. Yes.
So till now, what we get? We have some module capital M, capital N. Okay, and we have we, we have constructed new module M tensor N. Okay, M tensor N, which is generated by the elements of the form small n tensor small n. And we have some bilinear map G such that this m comma n goes to m tensor n. It's a bilinear map. Okay. Till now we have done this. This is a bilinear and this is some bilinear map. Okay. Now go back to the properties again. So till now do you understand what is going on?
Yes.
Okay. Now, so what do you get? So till now we get our G. Okay. Now we need to check this property is being satisfied or not, right? Okay. What is the property? That is, if we have any module P and any bilinear map, then we should get a unique map from P to P. Okay. That is to say, let me write it down. So that is to say we have some bilinear map F is bilinear, and some map is, then there should exist unique map F dash such that this commutes. Okay. How to approach this? And remember, this M tensor N is nothing but some kind of quotient. Okay. So how to get this done? Think about it. It is not difficult now, because M tensor N is something C by D. I mean, it is something inside quotient, some kind of quotient, and C by D is constructed from M cross N. So how you will get this done? It is not difficult. Now it is easy. I mean, you know this thing. So, I mean, what you first need to do, you need to get a map from C by D to P, right? Correct? That for that, first you need to get a map from C to P such that, I mean, which can be factored through D. I mean, first you need to get some map from C to P, correct? But you have already some map from M cross N to P. But also you have one thing, that C is a module, I mean, is a capital M module whose basis is capital M cross capital M. So till now what you have? You have some map from basis to some random module, and you need to get a map from the module generated by the basis. So what to do? Think about it, is not difficult. I mean, I'm not getting any way how to do this. So what you have? So consider the vector space case. Okay. So you have some map from a basis. We have some map from the basis. Now you need to get the map from the whole vector space. So what you will do?
We map first the basis element where the basis element goes and fix them. After that,
Yes, tell.
I mean prescribe image formation. If we know,
Basically summation of RIVI goes to RIFVI, right? You are saying.
yeah,
So same thing, the same construction will work here. So this is what? Suppose you have map from M cross N to P, small f, then you will get a map from C to, sorry, you will get a map from C to F tilde. Okay. Now, okay, and that is how the map F tilde is defined. F tilde of small n comma n is defined to be M comma n. That is F tilde of summation AI MI NI. We are defining it to be summation MI F MI comma NI, right? In this way we have defined the same in the vector space situation, right?
yes. Here, what is the tilde map? Tilde C to P, and C is the element of M cross N.
P is not element. P is the
Is
free module. P is the,
okay, free model.
yeah. So I mean here we are extending the map, and the extension is denoting by F tilde. Okay.
Okay.
I mean, so that is, I mean, this is the thing, right? So that's the extension. Okay. Now, since F is bilinear is given, so it is not difficult to check that F tilde is bilinear. It is not difficult. Okay. You can check it. Actually. It is not difficult. Now, since F tilde is bilinear, so F tilde of x1 plus x2 comma y is equal to F tilde x1 comma y minus f plus F tilde x2 comma y, right? With bilinearity. That is F tilde of x1 plus x2 comma y minus x1 comma y minus x2 comma y is equal to 0, correct? Everything is from binarity, right? Similarly, f tilde of x comma y1 plus y2 minus x comma y1 minus x comma y equal to 0. Similarly, f tilde of ax comma y minus ax comma y is equal to 0. F tilde of x comma y, sorry, x comma ay minus these things are 0, right? So this implies what? If so, look, if each and every these elements, these underlying elements are all generators of capital D, right? And F tilde, each and the map F tilde sending each of generator of capital D to 0. This means what? This means F tilde, so we have the map P to P F tilde. So now since sending capital to 0, so we are getting some well-defined map C by D to capital small p such that F tilde compose Q is equal to small f, right? Understand? I mean, do you understand this thing? This is nothing. I mean, just map a small f tilde sending each generator capital D to 0. So this means what? This map C by P is factored through, this map C to P is factored through C by D. Okay? You understand? Please don't hesitate. Do you understand what is going on?
Just scroll down the page once. I scroll up. Okay.
So, so now do you understand what is going on?
Yes.
So this means what? F dash compose Q is equal to F tilde, and Q is the quotient map, right? So F dash compose Q x comma y is equal to F tilde x comma y, and F tilde x comma y is nothing but F of x comma y, right? And this Q of x comma y is nothing but what? X comma y whole bar, and this is nothing but F dash x tensor y is nothing but F of x comma y, right? So we are getting, so from this relation we are getting this. This means what? This means that we have some this small a, okay, and we have that m tensor n and g. Then we are saying this map f tilde, that is f tilde of x tensor y is nothing but f of x comma y. Okay, this is what it is. So that is this diagonal commutes, and obviously this map f dash is linear by obvious reason. So that's all it is. So that's the first portion of the property. Do you understand?
Yes.
Do you have any confusion till now? I mean, obviously I know it's confusing, but Till now, what we have discussed, is there any confusion inside?
No, please scroll down, scroll up the page.
Yes, okay. So whenever you finish the writing, please tell me. I'll find out as we back with some minutes. Hello. Hello. Miss.
Sir, scroll up the page
Yes.
slightly.
Yeah. Yeah. And you have those you have the
Rama, yes, are you here?
okay. Yes, yes. Ah, yes, same as
Hello.
180.
Yes.
Yes. Do you sit for examination for this algebra one?
Sorry?
Uh, s- do you sit for examination for this algebra one by the end of this October?
Yeah, I have taken the exam.
Okay, okay. Which class do you read? I am master's first semester.
Oh no, I'm not a student.
Oh, okay. मतलब
Uh, I I am 2015 pass out actually.
master's pass या
Yeah, MSc in mathematics.
which university?
Mysore.
Mysore. Are you from Kerala? Okay.
No, Karnataka.
Karnataka, Karnataka. Okay, okay.
You are from?
I'm from West Bengal, Kolkata.
Okay.
Okay, okay. Very good. And are you prepared for NET and PhD? Yes, my entrance exam.
Yeah. For no, just it's been a long gap. So
Yes, yes.
I just
Gap ki
wanted to
first
start
interest is
towards.
ultimately matter.
Sorry.
Your interest in subject is ultimately matter.
Hmm. Yeah. Correct.
Yes, you can discuss some problem with me. That would be benefited both uh, for me and you.
Yeah. Sure.
I have also taken Gallery's course and other topic in NPTEL along with two
Oh.
courses are running parallelly.
Okay. Okay.
Okay.
So all those examinations will be on 29th only, I think.
Yes, yes.
How are you going to write both the exams?
No, I am sitting for examination only Gallery's theory.
Okay, not for this.
No, no, not for this, but I am seriously uh, reading for this course also.
Okay. Actually, my husband is a maths PhD, so he has taken Galois theory.
Oh, okay, that would be benefited for me, and you can contact with me, but for my for your that would be my pleasure.
Yeah, I'll talk to him and let you know.
Okay, 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 okay. Thank you. Very, very, very good. Sir, scroll down the page. Yes, yes. I have written, noting down that.
Yes.
Okay, sir.
So, so till now what we get? Till now we will get that if we have some a module m cross n, I mean mn into m to a module, then we'll get some another module named the tensor product of m tensor small n, and there is a bilinear map small g from sending m comma n to small m tensor small n, having the property that if p is any a module and f is any bilinear map, then there exists a linear map f dash such that this diagram formates. Okay, and f dash is given by f dash x tends to is equal to f of x power y. This thing you need to remember always while solving problems with the tensor product. Okay, so and also do note one thing, that there is also second part of that proposition, but right now we are not going to the second part. First we after this first part we shall start with some small problems, some basic things, then we shall go the second part by today or by next. Okay.
Okay.
Okay. So in the tensor product we have the following properties. So where are those ones? Yeah. So tensor product satisfies these. I mean, sorry, these are the relations. What are the relations? I mean, these three relations. These are the first thing we need to remember always. Okay. And second thing is that, okay, so we have seen that x uh, x1 plus x2 tensor y is equal to x1 tensor y plus x2 tensor y, right? So if we put 0 both sides, this implies what? 0 tensor y is equal to 0 tensor y plus 0 tensor y. Okay. This implies what? 0 tensor y is equal to 0. This is one relation. Okay. I mean 0 tensor y is equal to 0. It is something of something, some kind of obvious thing we should have, right? Similarly, we will get y tensor 0 is equal to 0. Okay. Now, mm, C. Now, uh, okay, so okay, so now, so suppose we have m equal to z, n equal to z, okay, and both are obviously z modules, okay. Then theoretically we have some map. I mean, theoretically we have some model z tensor taken over, okay. Now the problem is that, I mean, one obvious problem is to determine this z tensor z in terms of something known module, okay. So soon you will see that this z tensor z, tensor taken over z, is isomorphic to z, okay. So first this type of problem we first need to solve, okay. So for that, what we, I mean, do you understand what we are trying to do? We have m equal, suppose m equal to n equal to z, okay. So we have some z tensor z. By those properties and theorems, we have z tensor z, okay. But in order to practically work with z, I mean, in order to practically work in z tensor z, it is always better to understand z tensor z is isomorphic to something known or not, okay. So the thing is, z tensor z is isomorphic to, yeah, z tensor is isomorphic to the known ring of integer capital Z, okay. Do you understand? This is what we will now prove. So claim is that z tensor z isomorphic to Z. Do you understand?
Yes, yes.
Yeah, this is what we will prove. So for that, what to do? We need to now try now listen carefully. For that, we need to have two maps from z tensor z to z and in reverse direction, right? Okay. Now from z tensor z to z, it is difficult to construct some map because left side is quotient of some big thing. So directly we can't construct any map directly. Here we know to construct at least a map from z tensor z to z. I mean, from something m tensor n to p. In order to construct some map, we need to first make some bilinear map from z tensor z to z. Let me explain. Suppose you want to make some linear map from this. Suppose we want to make some linear map from m tensor n to p, okay. But by those, I mean, but there are big relations, okay. That's why first we need to make some bilinear map from m cross n to p. Then this bilinear map induce a map from m tensor n to p. This is what we need to do here. Do you understand?
Yes. I mean, sorry. You mean uh, M cross from M cross n we cannot construct a
Cross.
direct map. Direct
It is m tensor. It is not. It is m tensor. Okay. It is not.
M tensor from M tensor n we cannot. Hardly can do construct a map from this. Rather it would be easier if we construct a bilinear map, and that should be induced by linear map n.
Right. Hmm. So so first we will, so first we will try to get some map from z cross z to z, which is bilinear. This is what we need to do first. Understand? So what is the
Yes.
obvious way? M comma n goes to m n, just multiplication. Okay. Yeah,
Yes.
integer multiplication. Now, if you call this f, first check that f is bilinear. First check that f is bilinear map. This is some map from Z cross Z to Z. If we can show that f, I mean, if we check that f is bilinear, then this f induce a map from Z tensor Z to Z. Okay, that's all it is. So first check that this map more or less is bilinear or not.
Yes, yes, bilinear. Satisfy those three conditions.
Yes, so it is bilinear. So that means what? This small, I mean this map F induce a map Z tensor Z to Z, call it F dash. And what is this map? I mean, look, we have seen the same thing. What is this map F dash? This is the map F dash of x tensor y is equal to fx comma y. Okay. So same here, f dash of m tensor n is nothing but f of m comma n, which is mn. Okay. So this map is f dash is from z tensor z to z. M tensor n goes to m comma n, m into n. Do you understand? This map f tilde is getting from the what? From the property. Till now, do you understand?
Sir, here last line from the property.
Look, yes, let me repeat. So so now this portion. So what we have seen that we have, I mean, here we have already seen, right, that n cross n2 map p is smaller, then we will have some map f tilde, f dash, such that this commutes, and f dash is given by f dash of x tensor y is equal to f of x comma y, right?
Yes.
So that's what it is. That is,
Okay.
in our situation, f dash m tensor n is equal to f of m comma n. This is what we get already, what we have seen already. And in our case, f of m comma n is equal to m into n. Do you understand the point?
Yes, yes, yes.
Yeah. So basically, we have the map from Z tensor Z to Z, m tensor n is equal to mn. And this, since this is getting from the property, so this map is small f dash is well defined. I mean, it is obviously well defined the way you are getting from the property. Okay. So now this map is well defined. Okay. Now the point is that this map is well defined. Now we are directly saying this by using the property. But if you are directly defining this map, then you need to check well defined separately, which is difficult, right? So
Yes.
that's why we are using the property in order to ensure the well defined of some map going through the tensors. Understand?
Yes.
Okay, so this is one direction map. What is reverse direction map? I mean, reverse direction, it should be, it is an obvious map. What is this? N goes to,
And goes, sorry, n goes to p cross q by p by q.
no, you need to give another map G such that composition is identity on both sides, right? So N goes to where? Such that composition will be identity on both sides. No problem, you are getting this for first time, so it's difficult answer. So, okay, N goes to N tensor 1, you can say. Look, N tensor 1 is same as 1 tensor N, right?
Yes.
So, it doesn't matter what you're writing, N tensor and 1 tensor, it doesn't matter, okay? Now, you need to check that these are inverses of each other or not, right? Correct?
Okay.
So, Gx M tensor N, this is by definition what? G of Mn. This is by definition Mn tensor 1. This is equal to N. So this is N out, Nm tensor 1. This is nothing but M tensor N. So GF M tensor N is equal to M tensor N. And similarly, f G small n is equal to f of n tensor 1 is equal to n dot 1 is equal to n. So this is equal to, so on both sides this is identical. So this implies f and g are inverse to each other, and this tells that our defined map small f is an isomorphism. Understand?
Yes. Scroll down. Scroll down one second. Yes, yes. How to see if G compose F is uh, fine and F compose G of N.
Sorry, can you repeat?
How to see
How to see?
how to see you have shown that G compose F M tensor N is equal to M tensor N. Okay, but reverse straight direction. Okay, okay. In cross one. Oh, okay, okay.
So do you understand?
Yes, yes.
Okay, one second. Actually, there are the future. Hello, hello, hello. Yes. Okay. What are you? What are you? Oh, yeah. You are at the last end of the second district. No, no. Yeah, that I was. Are you at the end of the street? No, no. Sorry for the inconvenience. Yeah, please. Sorry for this. Okay. So, do you understand how we are getting that? By the way, not
Yes, yes,
okay. So, this is. I mean, now do you understand why we need to use those properties?
yes. Directly, it was quite difficult.
Yeah. Correct. So now one thing is to note the following. Um, suppose okay. So just tell me one thing. So we have some isomorphism from Z tensor Z to Z, right? With some isomorphism, correct? Yeah.
Yes, yes.
So if we suppose I am now asking you that element one tensor one is zero or not. So what will you do? This element one tensor one is zero or not? Then what you will do?
Yeah, yes. It should be uh, mm, one, one.
Yes, it is one. So in the under the isomorphism it is non-zero, right? So
Yes.
that's why one tensor one is non-zero
Oh,
in Z tensor Z. Okay.
okay.
So this is one way in order to determine that some element of tensor product is zero or not, because the relation is quite big, so it is not possible that one tensor one belongs to that relation that the submodel or not. Understand?
Okay.
So let me give some similar examples. So suppose we have some element 2Z tensor one. Oh, okay. Now consider the ring. Leave it. Consider the ring Z tensor Z. Okay. Now in this ring, consider the element 2 tensor 1 bar. Now tell me, this 2 tensor 1 bar using those properties. I mean, not those properties. I mean these things. Using this, can you please tell that? Can you please comment something about 2 tensor 1 bar in Z tensor Z2? Can you do any comment on Z tensor Z2 in this? I mean, in that ring there is element say 2 tensor 1 bar. Can you tell whether it is 0 or not 0? I mean, don't always think of isomorphism. We have some properties also. Usually, a tensor distributed over some tensor is. I mean, product can be. Yeah, tell.
One bar is equal to one.
I mean, one bar means in Z2 we have one bar, right? That one bar.
Oh, okay, okay, okay. It is think as it is thought as the two tensor one bar plus 0 bar. We can write, and using the property first we break into the rule of the tensor.
You're saying this, but then I mean this portion anyway is zero, right? Two tensor zero bar, it is zero, right? By those by one by another property we have seen. If one part is zero, then tensor is zero. So then any other way.
Other property I have missed that portion on a property is not. I'm not
You have
seeing
missed.
this.
You have missed.
Missed to write down the property. I have written just one property
I
out
mean,
of.
if you could not write, please you should tell. I will stop. One second. What is which portion? Which portion?
Yes, here. Yes, yes.
Are you talking about this? No, no. I think you are talking about this portion. Wait. You are talking about this, right?
Yes, yes, yes,
Yeah.
yes.
Right. Then write. After writing, let's tell.
Mm, Last property. Yes, if we take, we have to use the that property a x tensor y is equal to a tensor of x and y.
Yeah. Right. Correct. So that is 2 tensor 1 bar is nothing but 2.1 tensor 1 bar.
Mm, Yes.
Okay, kindly wait. Actually, back up a moment. বলো হ্যালো কি বলো না না তোমাকে আমি আধ ঘন্টা পর ফোন করছি ঠিক আছে ক্লাসে আছি ক্লাসে বেশ বেশ ঠিক আছে so 2 tensor 2.1 is equal to this, so it can be the 1 tensor 2 bar, and in z2 2 bar is 0, so this is 0. So you are
Yes.
trying to say, right? Yeah. So this is one way of doing a property, but so look one thing in that, but what about, I mean, consider this thing, okay? Consider this tensor, and here if we consider the element 2 tensor 1 bar, then can you say anything about 0 or not? And try to understand whether this argument is valid, whether this argument is valid in 2z tensor z2. Try to see.
Mm.
Look, the thing is, here we have done something. I mean, the third line we have something like 1 tensor 2 bar. Okay, now the point is that 1 tensor 2 bar is not an element in 2z tensor z2, right?
Yes.
That's why this argument will not work in 2z tensor z2. Okay, so in 2z tensor z2, in this way you can't say anything. So for this also, I mean, in 2z tensor z2, if you wish to determine the element 2 tensor 1 but is 0 or not, for that also you need to use that property. How to use it? So what we will do, we will make some map from 2z tensor z2 to z2, and we will see that one under this map here, 2 tensor 1 bar goes to some non-zero element. Okay, if this we can show that 2 tensor 1 bar is a non-zero element in 2z tensor z2. Do you understand what we are trying to do? I mean, what we need to do? Look, in 2z tensor z2 to z2, where we shall construct some map, a linear map. Okay, and
Yes.
we will in such a way that 2 tensor 1 bar goes to some non-zero element under this linear map. Then obviously 2 tensor 1 bar is a non-zero element in 2z tensor z2, right?
Yes.
So for that, how to do? So first we need to make this map from the uh, from the property. So we are defining 2n comma x bar goes to nx bar. Okay,
Mm.
check that f is bilinear map. Okay, so it is obviously it's not difficult. Now since it is bilinear map, so we will get some map from 2z tensor z2, which is linear to z2, and this map 2n tensor x bar goes to nx bar. This is a well-defined linear map. Okay, you understand? We are getting this by property only, nothing more than that. Understand? Yes or no?
Yes. Yes.
So, so what? So, so under this map of what 2 tensor 1 goes 2 tensor 1 bar goes to 1, which is a non-zero element. So that's why 2 tensor 1 is non-zero in z tensor z. You understand the argument?
Goes to, yes. Yes.
So this is way we can. This is another way we can say that some map is zero or not, some element is zero or not. Okay. So these are the basic things that we can do directly using the property. Now tell me, do you have any doubt in mind? I mean, of course, you might have some doubts because this concept is quite abstract. Now tell, do you have any doubts? Don't hesitate. You are not disturbed from this tensor product.
What are the motivation in behind the behind such rigorous property of tensor product after the free module?
Motivation. Actually, tensor product is used as a tool in topology. Okay. The point is that if you, I mean, unless and until you get in that portion, you could not realize the power of tensor
Utility of
product.
this,
Sorry,
unless till I have read the topology that cannot connect this, but
I mean,
it
it is
is
not.
utility.
No, it is not connection. It is all about the power. I mean, the tensor product has a extreme power in the topology. Without that, many things cannot be done. So, I mean, that's important. But directly, if you are directly trying to find the motivation, then it is difficult because it, I mean, it starts with some very abstract idea, some properties, right? So that's why it is very difficult to get motivated initially. That's all.
Sir, in Galois theory, we have so-called idea that the root of origin of modern such group and field structure are lying in the theory of Galois. There are but group are previously arise or after the theory of Galois it is arise.
Actually, thing is, this thing has been arranged many years ago. But Galois theory formalizes each and every concept. That is the point. I mean, you have some concept, but you need to formalize it. Galois theory formalizes those things.
Okay.
That's all. Okay. So, I mean, have you studied Galois theory?
Yes, and parallel course were running by Dilip Kumar Patil sir, Dilip P. Patil by IIT Bombay.
So, how that was going?
Uh,
I mean, how? I mean, how? I mean, how that course is for you? I mean, how you like this course or not? How? What?
yes, I'm liking and there is a ma'am to solve some conceptual problem in Sunday as like you. Fine.
So just tell me one thing. You are in MSc, right?
Yes.
MSc first or second year?
First.
Okay. So next, what is your planning? Some research or some other directions?
I have I have been liking to work with algebra and topology, their interplay.
Okay, that's nice. Oh. So till now, what have you started in topology?
Topology and basic topology and where fundamental group just starting.
That's good. So by the way, you are in which university or which college?
University of Kolkata.
That's good. Hmm. Okay. So, so do you want to do your research in abroad or in India?
Yes, sir.
I mean, do you want to do your research in abroad or in India?
Uh, I have not determined. So if opportunity will arise, then I have intention to go abroad and some university where the algebraic topology and this and algebra are not quite rigorously taught there.
Look, the thing is, I mean, thing is, you are going to do PhD after 1 year, right? Okay. So I mean, so don't expect that you will get taught those things rigorously. You have to understand those concepts by yourself. Okay.
Okay.
I mean, the only you can expect help from your guide or from a supervisor, but don't expect like this concept will be taught rigorously from the respective instructors. Most it is, I mean, it is almost rare. Usually, it is not rigorous. They will tell you the concept, and you have to. It is most probably there are many occasions that you will not. I mean, the concept will not get into. You just they will tell that result from this chapter, something like that. Okay, so you need to read the theory rigorously by yourself. Okay, so
Sir, what is the difference in on a research life and research study and up to that point we have studied masters and bachelors. There is teacher teaching some lessons and we have solving assignment and then submitting and PhD is that kind of study or different something.
the thing is, in PhD, there is coursework. You obviously know, I guess, right?
Yes,
So
coursework.
coursework is 1 year now. Coursework obviously there is exam, semester, etc. So that's going to natural way. So there is
Okay.
nothing more than that. But in up to second year, suppose I assume that you are going with the algebra direction. Okay,
Hmm.
so obviously your supervisor will ask you to read some books, some topics up to this chapter. You need to present those. I mean, the point is that in MSc, the instructor will teach you, but in second year on PhD onward, you have to read those things by yourself and then ask doubts from your guide to your guide or supervisor. Okay, I mean,
Okay.
on PhD, you should not expect even that that your supervisor will teach you rigorously. If it happens, then you are fortunate enough, but usually it does not happen. Okay. And
Yeah.
second thing is that in PhD means what? You need to solve some problem, right?
Yeah.
And solve some problem is if this problem has not been solved by anyone else previously. Okay. So the first point is that it is very difficult to understand that the way you are thinking to solve the problem is actually feasible or not. I mean, is it possible to solve that problem in that way? Is it possible or not? First, you need to understand. Now, of course, as a student, it's not possible to understand. So, there your guide will play a role. Only he or she can guess that whether the problem is solved in this direction or that direction. Okay, that is not easily possible by some students. Okay, and of course, there is a matter of uncertainty. I mean, you need to start. You can start the problem, but nobody knows whether this problem is actually solved or not. But because you have seen many theorems like this problem or this thing can't exist, so there is a point
Yeah.
of unsolvability. So that's the another thing that this thing something can be solvable or not at all. So that also uncertain. So that is the difficulty actually. Okay,
Hmm. Yes.
and also the thing is that since you are trying to get some solution of some problem. So you need to get updated with the corresponding literature. That is, who else in the whole world are working with this problem. If yes, then how much is the progress? What are the new results are getting? Now you may ask how you are getting this. So there are many websites. There are many research get website Google Scholar. You need to get over to website scholars in order to get the updated result regarding that topic also. Okay, so that is the difficulty. I mean, not the difficulty. I mean, it is the part of PhD. That's the point. Okay,
Yes. Yes.
it is not always reading books. There is something more you need to do. That's the
And duration depends on the student also. Duration of the PhD, how
it
much long
depends. It depends on
time?
the problem also.
Oh, okay, okay,
Okay, okay. So it is already 9. So let's stop here. We shall continue the tensor product in next week. Okay.
okay, sir.
Yeah.
Thank you. Good night, sir.
Okay. I'm leaving the call.